get started. So, so I'll just very briefly introduce why we're here, and then I'll leave it to John and Drew to kind of introduce the two groups. So we just, serendipity, we've got one of the Global Water Futures teams is focused on forecasting. We had a meeting a couple of weeks back. We thought it'd be a good idea to get caught up on kind of what's happening with the Treasury Board submission proposal that's being implemented right now. Those of you who know me, I'm the executive director of the National Hydrological Service. We've got funding to do a lot of stuff in the Water Survey of Canada, but we also had funding to develop a national framework for flow forecasting, basically. And Vincent's been kind of leading the charge with the folks at CMC, our numerical weather folks. And so our little forecasting team in GWF was looking at getting updated. So we thought that was a good idea. And then out of the blue, Drew came up with, hey, can we get an update on what's going on in Canada? And we thought, well, hey, we killed two birds with one stone here. So we'll have a bigger meeting. And then actually Martin Clark suggested maybe we open up to the bigger group of the core modeling group within the GWF framework. So here we are with a whole bunch of people. So it turned out to be a way bigger meeting than the 6 or 8 we had originally thought of, but that's great. And so I thought it'd be good to have start with John to describe a little bit about GWF, a little introduction for 5 minutes, and then Drew can talk about the work they're doing with the Powell Center group. And then we'll start off with Vincent giving the first talk, and we'll move off. So I'll ask people to please do your best on putting yourself on mute if you're not talking, and Pravin will kind of lead the whole thing in terms of the logistics and moving people forward. So with that note, I'll start with John to maybe introduce GWF and a little bit of background, and then we'll go to Drew or after. So thanks.
Okay, great. Thank you, Al, and thank you, Drew, for inviting me to the meeting. This is, as Al mentioned, this is fortuitous in many ways. There's a long-standing collaboration between a number of Canadian universities and the Department of Environment and Climate Change Canada on working towards improved prediction across Canadian river basins with an eye to larger areas as well. And as part of this collaboration, which dates back to the early 1990s through the Global Energy and Water Cycling Experiment, we proposed to the Government of Canada in 2016 that they fund a program we call Global Water Futures. And this they did, and that was marvelous because it allowed us to fund 190 professors at 18 universities across Canada, who have subsequently set up 64 research projects dealing with everything from eDNA to indigenous traditional knowledge to water and health to extreme events, from high-resolution atmospheric modeling to large-scale hydrological modeling to small-scale hydrological processes, some focusing on lakes, some on permafrost, some on glaciers, some on soil, some on agriculture. Water quality is a big part of it as well. And then a feature part of Global Water Futures is the core modeling program. So Global Water Futures involves roughly 970 postgraduate students, researchers, technicians, and others on the program. There are 60 observatories, field sites across the country that are instrumented in some way and providing data by which we can test our models and calibrate and parameterize them. And but the largest core team is the core modeling team, and that is led by Dr. Petronero and Dr. Martin Clark. It has a structured approach, including aspects of forecasting and geospatial intelligence, future hydrological modeling, current generation hydrological modeling, water resource modeling, water quality modeling, atmospheric driving data. So you get the picture there. And roughly 40 researchers working on this program right now. Many are postdoctoral fellows, others a bit beyond that, so at the research associate level. So the program is for Canada, very large, and has allowed us to make great progress on models. Some in direct collaboration with Environment Canada, so trying to make contributions of algorithms and information and testing of the GEM hydro system that you'll hear more about today. Others in working with that with Environment Canada on the development of the mesh hydrological model, and then collaborating with Environment Canada on development of new hydrological models as well. So it's been a very successful program so far. I think 1,700 publications coming out at this point. So and we're just halfway through it. So largest R&D expenditure in the universities in Canada on water in our history, and a very active core team that's tightly tied in and integrated with Environment Canada's modeling systems and modeling structure. So this collaboration with the Powell Centre is of particular interest. John Wesley Powell is a distant relative of mine, and there's a statue of him in the town where my grandparents lived. So, and certainly his great contributions to the development of water resources in the American West are well known to all of us. And we have this wonderful common interest in the Great Lakes region, from its groundwater to its lakes to its climate, and so that is an area where Canada and the U.S. should excel at working together. So I want to thank you all for joining today. I wish you great luck. I'll stay on this as long as I can. Unfortunately, we have another meeting scheduled in Canada that I'll have to attend in a little bit, but we'll carry on and pass it over to the chairs. Thank you.
Okay. John, good to hear from you, and Vincent. I'm sure you're eager to get started with the technical parts of the program, so I'll be very brief here. My name is Drew Grunewald. I'm an associate professor at the University of Michigan, and many of the folks on the call today are, as John mentioned, part of a project that is being led by the United States Geological Survey Powell Center. This particular project was just one of a handful selected as part of their annual program, in particular to improve groundwater representation in Great Lakes regional land surface and lake models. And there's two important components to the project. One specifically deals with the question of how can we work to improve and demonstrate improvements in representation of groundwater in state-of-the-art land surface numerical models. And that's one of the three pillars of our project. So we're at a phase in the project right now. When I say we, I mean myself, three other co-PIs on the project, including Sandy Eberts of USGS, Julie May of the University of Waterloo, and also Howard Reeves of USGS, along with 15 other key collaborators on this project. We are just in the midst of launching the technical background components of this project. Tomorrow, we'll be doing a series of workshops on the background of technical modeling in the Great Lakes, but it is just wonderfully serendipitous that Al, Vincent, and others were organizing this workshop and graciously offered to invite us to listen in on this workshop and learn more, particularly about the wonderful Canadian land surface modeling work that's being done. So thank you, Vincent and Al and Pravin and others for extending the invitation and helping coordinate the technical logistics. We're really looking forward to this workshop, and I just want to thank you again.
Okay, thanks, Drew and John. Appreciate the comments. I think we're ready to start, right? So I'd rather not go through introductions for everybody, just because it's going to take forever. Yep. So I'm sure most people know each other, and if not, Google them, and you'll find out who they are. So Vincent, the floor is yours, and Pravin's there to assist, right? So I'll let you kind of lead the meeting from now on, because it's all your folks, and the agenda's out, and so yeah, we'll see how it goes. Thanks very much.
Right. I'm right in. I'm hoping you can hear me and see the slide. So, let's start. My name is Vincent Fortin, and I work at the Canadian Meteorological Centre. I'm part of the Meteorological Research Division, and today I'm going to introduce you the hydrometeorological prediction systems that we run at CMC. And also the people supporting them. We'll get to that a bit today.
I can see the slides, but the sound is a little bit poor. It's very hard to hear.
What I can do about this, I don't even see the controls for sound right now. Perhaps I can switch microphone.
So is this microphone better?
Yeah, this is better.
Okay, so I'll go with this microphone. First, who we are, the Canadian Meteorological Centre. That just the term creates a lot of confusion. It's a building, really. It's in Dorval, close to Montreal. And in this building, you have people from 3 organizations. The Meteorological Research Division, which is part of the Science and Technology branch of ECCC. The Canadian Centre for Meteorological and Environmental Prediction, which is part of the Meteorological Service of Canada, also a branch of ECCC. And Shared Services Canada, which provides the IT support. So essentially, we each have a floor, while CCNP has 2. So there is research, development, which is mostly about technological transfer, but the development folks assist with the research and assist with the operations. And then there's operations which are responsible for the 24-hour, 7-day support. Today's presentations are given by Meteorological Research Division scientists, but the work is really collaborative research and development activities that are done with CCNP, but also with the National Hydrological Service. So I thought it was useful to look at the org charts just briefly, just to mention that we really have 2 parallel structures, one for research and one for technological transfer, with groups in each in research and development looking at environmental processes, and in particular ocean, surface, and hydrology. So there's a hydrology section in research and another one in development, and we will really work hand in hand, but these 3 groups, ocean, surface, and hydrology, are important in the development of the hydrometeorological prediction systems. There are also structures for atmosphere forecasting. I'm not going to talk about that, but they are also, of course, very important. And there is significant funding provided by NHS, by the NHS Transformation Initiative, to these 2 sections in research and development for hydrology. Again, it's really a collaborative research, development, operations effort between NHS, CCNEP, the Meteorological Research Division, but also academia. So universities, of course, have a very important role to propose and test ideas for improving models, and also to train students, right? So the NHS Transformation Initiative is really organized this way. So the scientists that will be presenting today in hour 1, we'll hear from Tikra Kedaouria on precipitation analysis, then from Milena Dimitrievich on surface and precipitation reanalysis. In hour 2, we'll hear about the National Surface and River Prediction System, also known as GEMHydro. And we'll hear we'll have a talk on land surface assimilation, data assimilation from Camille Garneau. Then Vincent Vionnet will talk about land surface modeling, and Etienne Gabory on reservoir and river routing. In hour 3, I'll come back to talk about our water cycle prediction system. Camille Garneau will come back to talk about small lake modeling. Pascal Matt will talk about hydrodynamic modeling, and we'll have the last talk by Sylvia Innocenti on ensemble forecasting. The prediction system, so there are lots of acronyms today, so it's part of my job today to introduce you to all of these acronyms. We'll have a quiz afterwards. Just kidding. So in hour 1, you'll hear about CAPA, the Canadian Precipitation Analysis, and the Regional Deterministic Reanalysis System, RDRS, which is used to go back in time with our prediction systems. And then in hour 2, you'll hear about the National Surface and River Prediction System, which is a Canada-wide, high-resolution offline prediction system for surface, lakes, reservoirs, and rivers. It provides 6-day deterministic forecasts, and soon we'll be providing 30-day ensemble forecasts. In hour 3, you'll hear about the Water Cycle Prediction System, which is a 2-way coupled atmospheric, surface, river, large lakes, and ocean prediction system. It provides 3.5-day forecasts for the Great Lakes and the Gulf of St. Lawrence. You'll also hear in hour 3 about the operational hydrodynamic prediction system based on the H2D2 model, which provides 2-day deterministic forecasts for the St. Lawrence River at the moment, and an ensemble forecasting system is under development. So just I'll briefly introduce each of these systems in a few slides. So let's start with the analysis and reanalysis systems, the Canadian precipitation analysis, and the regional deterministic reanalysis system. So the Canadian precipitation analysis, or CAPA, is the most mature of the systems we'll present today. It's been operational since 2011. And it's a system that merges various sources of information on precipitation, so observed precipitation, to create a quantitative precipitation estimate covering all of North America. And it also, there's another product covering all of Canada at higher resolution. So on the left here, you see a plot showing for a particular day in 2020, the gauge data that was available to us in real time. The colors correspond to the intensity of the precipitation over so the amounts over the last 24 hours. So you see that in some regions, there's a fairly good coverage, and you can guess at the precipitation structures from the gauge data. But in most of Canada, it's really not sufficient to provide a good estimate of the spatial structures. The analysis product combines these in situ observations with weather radar, satellite data, and a short-term weather forecast to create a picture in which you can more readily see the spatial structures, and we have proved that it actually verifies better against independent data. It's also very robust. It's always available. If one source of information goes down, the others take over essentially. So you can see, for example, there's a spatial structure here just east of Lake Superior. That's not obvious at all from the gauge data because we have a gap here in the data coverage. You can see also a hurricane that's going to hit, well, it was hitting Bermuda at the time. So you see this one section here in the middle of the ocean, but you can obviously see the spatial structure in the analysis. So the regional deterministic reanalysis system, essentially the initial goal was to be able, with CAPA, this is a real-time system, but there's demand to go back in time to as early as 1980. So we've devised a system to do that, called the Regional Deterministic Reanalysis System. But really, it's more than a precipitation analysis system. It provides information on the atmosphere, on the surface, the hydrology, and it provides that information on a grid, on a 10-kilometer grid, and it has a hourly time step. So Milena will talk about that later. Then I have a few slides on the National Surface and River Prediction System, also known as GEM-HYDRO. GEM-HYDRO is really the name of the model, but the prediction system is larger than the model because it includes the data assimilation system, pre-processing and post-processing as well. As part of the National Surface and River Prediction System, you have the Canadian Land Data Assimilation System that provides initial conditions. You have high-resolution land prediction systems that predict the state of the land surface, and hydrological prediction systems that predict the state of lakes, reservoirs, and rivers. So how does it work? Well, essentially on the left here, you have a bunch of observations from satellite radar, in situ gauges, water level gauges that go into a data assimilation system, providing grid analysis that are used as initial conditions for numerical models that forecast in the future the state of the land surface and river systems. And you get at the end 2D maps of soil moisture, so state variables, fluxes like runoff and stream flow on a national grid. Because it's fairly complicated to develop these data assimilation and forecasting systems, we've essentially split them in two. So we have a land data assimilation system that focuses on the state of the land surface, and a river data assimilation system that focuses on the state of reservoir, lakes, and rivers. And they assimilate different sets of observations. And the land data assimilation forces the river data assimilation system. And these systems initialize a surface forecasting system and a river forecasting system. So we've done that just to simplify the management of the system. So if we simplify this slide a bit, essentially we have a 2x2 matrix with on top the land surface systems, and on the bottom the river systems. Left is the data assimilation system, right is the forecasting system. So the land data assimilation systems and surface forecasting system are currently based on SVS1, which is our land surface model. And the river systems are based currently on the WATROUTE river routing model. This is the full picture that you'll see a few times today of the systems and the different variables that are exchanged between the systems, but it's really the same idea that I had here, just in more detail. So the data assimilation system, land data assimilation system is called CalDAS, and it provides information to a hydrological prediction systems named DHPS, for deterministic hydrological prediction system, in analysis mode that provides analysis through the same system running in forecast mode. And for the surface prediction system, it's called HRDLPS, high resolution deterministic land prediction system. But there are lots of details here, but remember perhaps this slide, which is much simpler. But you'll hear more about this one today. Why do we run our own land surface model? There are land surface models in the atmospheric prediction systems. The reason we do that is that the atmospheric models have horizontal resolution and also accuracy that decreases with lead time. So you have higher resolution for the first few days and a much lower resolution a month out. So the way we run our land surface model, because we run it offline, it's less costly, so we can afford a constant and higher horizontal resolution for the duration of the integration, which allows us to better detail the representation of the land surface. These are typical outputs from the model, from the National Surface and River Prediction System. So this is a 6-day out forecast, valid on September 23rd at 2.5 kilometer resolution. So you have a forecast of precipitation on the top left, a forecast of soil moisture on the top right, then a forecast of 2-meter temperature, bottom left, and surface runoff, which is an output from the land surface model. So there are very interesting features on this map. So you can see bottom left on an area with very little precipitation, very little soil moisture. This was at a time where there were forest fires raging in this area. This is an area that's fairly warm and no runoff. Here you have Hurricane Sally that had just hit in the southeast of the US. You can see it in the precip field, also in the soil moisture, so fairly wet. Colder and lots of runoff. Another hurricane was forecast to hit Canada, and it did actually. So this was a very good hurricane forecast from CMC. So we had lots of precipitation in the forecast, lots of soil moisture in this area, warmer temperatures, and lots of runoff again. An area here with precipitation, a bit of precipitation, relatively, well, no, not much happening in terms of soil moisture, but so fairly cold here, but with runoff, and that was due to snow melt. This is the corresponding stream flow forecast. So you're looking at flow on a log scale. It's quite difficult to see the details, so we can zoom in. So you see the rivers around Great Slave Lake. The color here corresponds to the magnitude of the predicted flow. And I can look at the hydrograph for Hay River. What you're looking at here is the over a set of 2 months, the one-day forecasts from that system. So for one-day forecast stitched together for 2 months to show the quality of the system. I have a few slides on the hydrodynamic prediction systems that we'll see today. So we'll hear about the operational hydrodynamic prediction system and the water cycle prediction system. So our hydrodynamic prediction system, based on the H2D2 hydrodynamic model developed by NHS, provides both a steady state solution and a 2-day forecast on using a finite element mesh. And it includes a wetting and drying scheme for flood mapping applications, but also for habitat modeling. And this is an example of a prediction for a major flood in the Lac Saint-Pierre area downstream of Montreal. That matches very well the aerial photography. The SHOP system can actually be driven by the surface and river prediction system. So it receives boundary conditions from that system. The last system I want to introduce is the water cycle prediction system, which is a fully coupled atmospheric, hydrological, ice and ocean modeling system. This one is fully operational with 24/7 support, whereas the National Surface and River Prediction System is still experimental. We hope to have it operational a year from now. Products are available on Datamart as flat files in NetCDF format, and on GeoMet, which is a web mapping service, web WCS, not web feature service, something like that. And the way this system works is that it starts with initial conditions provided by a global forecast of the atmosphere. We run a limited area model centered over the Great Lakes and the Gulf of St. Lawrence. And this atmospheric model is two-way coupled with an ocean model that represents both the Great Lakes and the Gulf of St. Lawrence. So the turbulent fluxes are over the lake surface and ocean surface are computed by the ocean model. But it also receives stream flow from a river routing model running at 1 kilometer resolution over the same domain. And the runoff is provided by the atmospheric model. The NSRPS river routing system is installed on all the watersheds in pink here. So from Yukon all the way to Newfoundland. But the water cycle prediction system is only running on this one area. So I'll stop there and pass it to Dikra, who will talk about the Canadian precipitation analysis in more details. How do I stop sharing?
So as she gets her slides up, Vincent, just if you want to answer any quick questions, a minute.
Yep.
I'm not sure. People can put their hand up, I guess. Pravin, you can tell, right? Or type something in the chat.
Yeah, so I'll be monitoring the chat. So I suggest that we have questions and answers through the chat as the presentations go forward.
Yeah, that makes sense. Okay, thank you.
And there's a bit of buffer time at the end of each hour to ask questions live.
Okay, perfect. Let's do that then. That's great. Thanks, Vincent.
Hello, everyone. I guess you can hear me and see my screen. I'm going to present you the Canadian precipitation analysis and the 3 subsequent systems that are attached to CAPA. So my presentation is organized on 3 parts. I'm going to show you the a quick overview of CAPA and the three configurations of CAPA, and then I will present you the innovation that will be available for the next operational systems, and how it improves the current system. And I conclude with the research and development project for CAPA. So the first quick overview is the configurations of CAPA. So currently we have three configurations. So two are deterministic.
We're still on slide 1, so perhaps you're not sharing the right screen.
I have only one screen sharing.
Okay. Yeah, okay, now it's working.
Okay, that's weird. It's when it's full screen that you cannot see the. Okay, so I'll continue this. I think you can see the whole presentation. Okay, so I just mentioned earlier the three configurations of CAPA. So two are deterministic. So we have 24-hour and 6-hour accumulation precipitation available at synoptic hours. So one is at approximately 10-kilometer resolution. So it's the regional precipitation analysis. So the RDPA, so the CAPA regional, and you can see it here, the domain in the orange the orange frame. We also have for deterministic precipitation analysis the high resolution version. So it's approximately 2.5 kilometer, and you have a smaller domain, but covering almost whole Canada here. And we have the last configuration of CAPA is the ensemble version of CAPA. So it is named HREPA, so the high resolution ensemble precipitation analysis. For the moment, it's statistically based, so we do not use an ensemble prediction system at that resolution, and we have 24 members with running for only the 6-hour accumulation and available also at synoptic hours. So more details on CAPA. So some of you may know that CAPA uses an OI, an optimal interpolation approach to do the analysis. So it means that it combines optimally the surface observation, the radar QPEs, so the quantitative precipitation estimates from radar, and from the forecast. So you can see here on the map the valid assimilated precipitation data for the surface stations in small blue, for the synoptic stations in orange. So those stations are used for the assimilations and for the verifications. And you can see here in gray the radar beam that were assimilated for RDPA. So here it's for the summer 2019. Regarding the forecast, so we use different forecasts depending on the configuration of CAPA. So for the regional CAPA, we use the regional prediction systems, and we use the 6 to 12-hour forecast window. For the high resolution, we use the high resolution prediction systems. And for HREPA, which is slightly a different system, we use perturbed precipitation field that are coming from the CalDAS national, so it's the land data assimilation systems. And we use also a different forecast window here, 0 to 6. So now I'm going to present you the innovation that were presented for the that were proposed, for the next operational system. So for CAPA, those innovations consist of adding or removing some data sets in order to improve the observation coverage and then to have better precipitation analysis. So those observations are of three types. So first we have the surface stations, and for the new operational systems, we are adding two networks, one in Manitoba and one in Ontario. The other observations is the radar. We are using more radars, and we are also including satellite data for the next operational systems. So I'm going to present you quickly the radar that are going to be added in the next system. So here you can see in blue the current operational radar that are assimilated in CAPA, and the orange one are the new radars in the USA that are planning to be added, and the green one are also new one that were going added in Canada. So we have a better coverage for the whole three systems that I presented earlier. Regarding the satellites, we have two types of innovations regarding satellite data. So the first one is concerned the cloud masks. We are using a new updated GOES version for those cloud masks. So those masks help us to clean the radar KPIs during clear sky conditions. But the most important satellite data that are going to be added to CAPA is the IMERGE early. So IMERGE is the integrated multi-satellite retrievals for GPM. So it's a very interesting data set because it offers us the possibility to add a gridded precipitation accumulation at approximately 10 kilometers. So covering the whole domain. And for the IMERGE early, we cannot assimilate those precipitation directly. We need to bias correct those precipitation. So here we are using the HRDPS, so the prediction system relative humidity, to correct bias in IMERGE. And you can see here on the map an example of for a valid time, the precipitation accumulation, the 6-hour accumulation across the domain. So you can see that we have a great coverage of precipitation above water and over the whole domain. So now I will jump directly on the added value of those innovations compared to what we have currently. So the first results concern the regional precipitation analysis for the summer 2019. And all the results that I'm going to present you uses only synoptic stations, so that the orange dot of the first map I showed you earlier, and it is an leave one out framework. So in red here, you will see also the innovations, so the stations, the radar, the GOES, the IMERGE for the systems that I'm showing. So here the RDPA, and the reference here is the regional precipitation analysis that is operational. So the first results concern the precipitations at 24 hours, and it also helps us to see the frequency bias here through the FBI, the frequency bias index -1. So here, if you we want to be close to the zero line here to say that we have no bias in our precipitation analysis. And on the x-axis, you see the different precipitation threshold evolving. And last point also on those figures is when you see the shaded gray area, it means that the differences between the systems are not significant. So here you can see that with our new innovations, the red curve is closer to zero for the small precipitation. We have a small degradation here for the two, and then we have a better performances for the other precipitation threshold. And when we move to the ETS, so the ETS is the equitable threat score. It helps us evaluate the skill of the precipitation analysis, and it is a very important score here. And the higher ETS, the better is the precipitation analysis. So you can see here that clearly for all precipitation threshold, we are considerably increasing the scale of the precipitation analysis here in the red curve. When we look at the 6-hour precipitation, we have pretty the same results, and now we have even less degradation of bias for some precipitation threshold. So less bias for the precipitation analysis and better scale. And we are actually reducing the false alarm in the precipitation analysis. So that was for the verification against stations, but there are also many interesting aspects to see when we add the gridded precipitation to be assimilated like iMerge. For example, we can see at precipitation accumulation maps. So here you can see the iMerge, the analysis for the summer 2019 accumulated over that period without iMerge and with iMerge. And here we can see the differences. And when it's green, it means that there are more water. But the more interesting thing is that we can see that we have different pattern of precipitations above the water bodies, so above the Great Lakes. Here we can see that something is happening, because in the past we do not have precipitation observation there. So it's an important, yeah, it's very interesting. The last aspect also of iMerge and the other innovation is that we are increasing the confidence across the domain, the confidence that we have in the precipitation analysis. So some of you may know that CAPA comes along with the confidence index. So this confidence index ranges from 0 to 1, and the 1 is, it means that we have a high confidence on the precipitation analysis for a given grid cell. So it means that we are ingesting much more observations at those points. So here you can see that the operational CAPA, regional CAPA, and you can see here that we have, it's in purple, so we are around 0.8, so we have a great confidence on those regions. But we can see also that we are green for many parts above water. So when we are green, so we have a confidence index close to 0. So it means actually we are using the forecast. There are no observation ingested there. And when we use the iMerge data and the new radars and new stations, we can see that we are dramatically increasing the confidence of the precipitation analysis across the domain. So now I'm going to present you the high resolution ensemble precipitation analysis available at 6 hours. So just a brief description of these systems. So HYDRODYNAMIC, currently it was developed to provide ensemble analysis to the CalDAS NSRPS, so to the land data assimilation system. So we can, so that CalDAS can therefore benefit from all the upgrades of CAPA. So in the past, and currently actually, CalDAS uses an embedded CAPA precipitation embedded CAPA system. So it is an old version without the radars, without all the new stations. So so subsequently the hydrology may not benefit of the old the innovation that CAPA may have. And HYDRODYNAMIC is was built using statistical approaches for the perturbations. So for the observation and the radar QPEs, we perturb them based on estimated observations errors that were estimated within the CAPA system. For the forecast, we are only randomly perturbing those precipitation fields in space so that we can represent the location errors in the forecast. So it was a brief presentation of this ensemble. So when we want to see so here you can see the impact of the innovations on HYDRODYNAMIC through these two figures. But yeah, so the first one here, so still the same color code, the blue and the red. So the red is the new system. You can see here the reliability diagram for the precipitation threshold 1 millimeter. I think I won't have enough time to describe these figures, but these figures help us to evaluate the conditional bias in the ensemble analysis. And as we are closer to this to this diagonal here, we increase the reliability in our ensemble. So we can see here that the red curve is slightly below. So we are degrading a little bit the conditional bias for this ensemble. So, but it is only for the 1 millimeter threshold. As we go up, we can see that this degradation is even less perceptible. And we have also here the Breyer scale score. So the Breyer scale score is like a MSE, so mean square error. Here we want that this score is as close to 1 as possible to have a better skill in the analysis. And we can see that here with the new system for different precipitation threshold, we are increasing the skill. So that was for the high resolution ensemble, but we have exactly the same pattern of results when we look at the HRDPA, because I'm not presenting the result regarding HRDPA here. So we have a slight degradation of bias for some threshold, but an increase of skill when we use those innovations. And now that was for the innovations that are planned for the next year, but there are also research and development for even further innovations cycle at ICCC. So regarding the assimilation system in itself, we're planning to use the regional ensemble prediction system to better estimate errors in the assimilation process. So now we have an operational ensemble prediction systems at 10 kilometers that is available. So we want to use that. An important aspect is the assimilation of the non-liquid precipitation to improve the confidence of the analysis during winter. So all the results I showed you earlier are only for the summer, and we do not expect as much gain in winter, as we do not assimilate I-merge during non-liquid precipitation, neither the radar QPEs. That was for the assimilation system, but we are also planning to add even more radars to increase the coverage, because some are already available and they need to be added to CAPA. And we want also to test the benefit of different radar products to develop at ICCC, which is Paltrad, and it seems promising to use that for CAPA. So I leave you with here the different access that you can have for CAPA. So the first one is the first link here is for accessing the data in itself. So we have the RDPA, the regional, the high resolution precipitation analysis, and we have also the HRDPA average, which offers the information on precipitation average per watershed. You can also have access to different viewers if you want to see for a given time step how CAPA looks like. You can see on the site of the Government of Canada here one viewer, and there is also another one here from the Midwestern Regional Climate Center. You can see the RDPA and its combination with the NOAA MPE. So that conclude my presentation for CAPA.
Merci beaucoup. Thank you, Dikra. There are a few comments and questions in the chat, so I invite you to respond while Milena gets set up. So to answer in the chat. Milena, can you share your screen? We'll continue with the reanalysis system. It is very much linked to CAPA.
Yes, can you hear me?
Yes, working.
Okay, do you see my screen?
Yes, but not in presentation mode yet. If you go to slideshow, it should work. Working.
Ah, it's working?
Yes.
And it's changing the slides, yes? Okay.
Yes.
Okay, so I will talk about the surface and precipitation reanalysis and Environment Canada. So this is a joint effort between research, development, and operations, and most particularly between Meteorological Research Division and Canadian Centre for Environmental and Meteorological Prediction from Environment Canada. And here I listed the people involved in the preparation of the article for this project. This project was initiated by the International Joint Commission under the International Watershed Initiative between US and Canada. And it is because of the increasing demands for long-term reforecast and surface reanalysis datasets at high resolution over North America. And surface reanalysis and atmospheric reforecast system allow us running the current models back in time. And for this project, we are going back to the 1980s. And it allows us to estimate precipitation even in the areas without or limited gauges and radar coverage, and also to provide a seamless reanalysis across Canada and US border, and to be available for the all Canada US transboundary watersheds, which is really for the hydrological application. And more generally, this project is useful for regional climatic studies, climate trend analysis, health studies, policy making, and others. So you already saw this schematic. So it is a methodology of our system. So we are starting with ERA interim, which was available when we started the project from 1980s to 2080s. So at the 80 kilometer resolution and every 6 hours. This was used to run first surface model called GEMSURFs at the 39 kilometer resolution, which is then used as initial conditions for the global deterministic reforecasting system at the same resolution, and atmospheric analysis is coming directly from the ERA interim. And then we are improving the resolution, going to the regional deterministic reforecasting system at 10 kilometers. And what is the most important is the surface data and precipitation assimilation. So coupling of the GEM model with the CALDAS and CAPA for the assimilation of the surface observations. So a little bit more on the configuration. So the global and regional component, both are done at 12-hour cycles, every 0 and 12Z, and we are doing 24-hour reforecasting. Then for the regional component, it is only for the North America. You are seeing the domain here at 10 kilometer resolution. It is 12-hour cycles, and the GEM forcings from CAPA CALDAS are prepared in 6 and 18Z. Time resolution of outputs of all of the system is 1 hour. After all that steps, we are also doing a posteriori 24-hour precipitation analysis, and we produce that for the period 2000 and 2017. So here is the verification from a regional reforecasting system comparing with the operational model outputs, which is RDRS, for the 2011 and up to 2017, because we don't have operational model outputs previously of 2011. So in this table, you see by columns, it's for winter, spring, summer, and fall. And for the different regions, starting with Alaska, Canada, Mexico, North America, and US, for the different variables, we have here pressure, dew point temperature, and wind speed. So if the box is red, it means that the reforecasting system is better than the operational model. And if it's blue, that is operational system is better. So you see that in most of the cases, the reforecasting system is better and in some instances and for some variables much better than the regional operational model. So here I'm just presenting you for the screen level dev point temperature root mean square error in the time series. So starting 2011 up to 2017. And we see in red is the reforecasting system, in blue is the RDPS, so operational model. And we see is from 2016 up to now, the performance of the model is the same, but going in the past, we see the reforecasting system is better than the RDPS. And this is mostly because we are using the most up-to-date model for running previous years. And the bottom graph, I show you the same dew point temperature for the North America, but this time just only from the reforecasting system, starting in 2000, because we don't have, as I said, outputs for the previous years from the operational model. And we see even if the number of observation is decreasing, going back in time, that we have a very similar performance for whole period. Here I will just say a few words about the CAPA 24-hour posteriori analysis, which is done in the post-processing once all the components of the systems are performed. And what are the observations that we are using? So we are using, as most of the system, SYNOP, METEOR, and surface aviation databases for the surface observation. And here particularly is the table for the precipitation. But in the 24-hour posteriori analysis, we have some additional networks. For instance, Quebec network, and most particularly in US, it's standard hydrological exchange format, which includes COCORA's data. And this database is only for the 24-hour accumulation, so it could be used only in the post-processing step. And this is like a major with the 21,000 station used from this network for US. And in Canada, we have adjusted daily rain and snow data, which came from, it's a climate network. It's approximately 1,500 stations for the 2000-2070 period, as also available only as 24-hour accumulations. I will just mention here that for the phase 2, which is from 1980s to 1999, we don't have a complete archive of surface observation available internally. So we need to rely on the integrated surface data, or ISD, from NOAA. This is a global data set of hourly observations, and it comprises of approximately 35,000 stations globally. And here I put it just a screen level temperature root mean square when we use this network as an input in our system. So here also just to see what are the improvements of the analysis when compared with forecast. So analysis in red, forecast in blue. In the first, in the upper graphs, I present the scores for the winter, and bottom is for summer. This is the whole period 2000-2017, and we have like a different scores. So here is the frequency bias index in the first row. Then we have equitable treat score, probability of detection next, and the fourth score is false alarm ratio. So we want that the frequency bias is then is closer to one, as well as the false alarm ratio. But for the ETS and pod, we want to have like a higher values. And we see that we have very big improvements for all of these scores. And the only exceptions is the probability of detection for the thresholds less than 2 millimeters, where our analysis is a little bit worse than forecast. But this is only for the winter. We have also scores for spring and fall, and this is the only degradation. And considering all the improvements that we have for other scores, we think that this one is acceptable. So here a few words about application of the data produced by a reforecasting system. This is the snow water equivalent anomaly. And starting this year in spring, it is the routinely produced once daily by the Meteorological Service of Canada. So anomaly is calculated with the RDRS analysis and 70 years of SWE anomaly from the reanalysis. And we see some, this is for this December 2nd, we see that we had some snow for the prairies and also I know in Labrador. This is even more application in hydrology. So this is water simulation of a stream flow in the for the total lake inflow of Lake Erie. And in black, it's those are stream flow observation. In gray is RDRS with CAPA, and red is the reanalysis, which includes CAPA also. So we see quite similar performance, but few peaks are better captured by the reanalysis than RDRS. So what are our current developments in the project? Our top priority is to submit an article in the Hydrology and Earth System Sciences journal, and the article will be available right away when submitted. So this is an advantage, and we think it will be in January. So the status, you already see the result that I showed you. So we completed the regional deterministic reforecasting system component for 2000 up to 2017, and also CAPA posteriori is completed, and the data will be distributed through CASPAR in NetCDF format. For the current year, our developments will be in operation. We need to start the production for the years before 2000. The tests are already done, so we need to do the actual final runs. In research, we are concentrating to doing runs with a global reforecasting system for 2070 and 2080. With operational CMC analysis, and then to compare coupled regional runs started with ERA interim that we already have available against this version with operational CMC analysis. And also we think we will start in the next year tests with ERAS-5 and to update CALDAS with satellite data. And for now, we are using just the CALDAS in situ data. Our long-term plans stay the same, so we will continue to the evaluation of reforecasting reanalysis, and also once the whole period is completed, we need to produce a climatology and anomalies for the surface variables and also hydrological variables. So, as I briefly said, the public access to the reanalysis will be through the Canadian Surface Prediction Archives, which is developed through FloodNet. Here, I'm just giving the details about what will be available. So, starting with radiation, then humidity, pressure. We will have two precipitation fields, so one directly from the model, so forecasting, and other is analysis, and then temperature and the wind. And our long-term plan, it will be that those data would be accessible directly from Environment Canada through GeoMet project. And here is the new CASPAR platform, and a few of you probably know already. So we can select the variables and the region of interest. So it's all from me. Thank you.
Thank you. So again, please have a look at the chat for questions and answers on this system, and we will go to the talks on the National Surface and River Prediction System, starting with one on the Canadian Land Data Assimilation System, and with focus on the snow analysis by Camille Garneau. Camille, are you there?
Sorry. Okay. Are we not taking a break then?
Well, we're already running late, so I think we have to continue and have questions through the chat.
Okay. Sorry, I wasn't
Hopefully
ready.
We can.
I don't open. Sorry. It'll be there soon.
Yeah, so that's our break.
Yes. And obviously the computer is super slow. Okay.
Nobody panic, it's all good. Just to thank the first two speakers, those were excellent talks, and it really gets a lot of people caught up on what we're doing with reanalysis and the analysis. So that's great information. And I mentioned in the chat that this is being recorded, right? So people can go back to the talks if they want to. We'll send you the links and try to figure things out. And there might be some value based on, and after all this, maybe we'll work with the forecasting group to develop a series of links or something for all this stuff so that people can access GeoMet and other things so they know where everything is. And we'll put it on our GWF site and move that forward. So that's something to consider. So,
yes.
And Camille, you're going to talk next, right?
Yeah.
Yeah. So I'll be showing my the presentation from Firefox because the PowerPoint is taking quite a bit of time to open. So let me know if it's correct, if you see it.
Not yet.
No, I have my colorful ball that's spinning, so it's just thinking yet. So I'll just start introducing the subject. So I'll be talking about, let me know when you see anything. I'll be talking about CARDAS. CARDAS, if you recall, is the land data assimilation component of NSRPS. It's a big machine, so I'm obviously not the only one working on this. Marco Carrera and Bernard Bilodeau are working quite a bit on it. I'm more focused on the snow component of CARDAS. So that's what I'll be briefly presenting CARDAS and then talking more about the snow component and the innovations that we introduced recently. Do you not see anything yet?
Yeah, we can see the presentation, but it's not in PowerPoint mode.
Yeah, so just go to
wait, my PowerPoint is not
mode.
yet. Wait.
Yeah, but presentation mode would work as well.
Okay.
As you wish.
PowerPoint. Okay. How is that?
You can still see the slide, but it's still not in the PowerPoint mode.
It's just a bit of a lag, I think. So just.
Okay.
Yeah,
how's
working.
Great.
Merci.
Do you see the Zoom windows or not, or is it just me?
We see the correct one, the presentation.
Okay, perfect. Okay, so as I said, CADAS. The goal of CADAS is obviously to produce the best land surface estimate. And how we do this is through the assimilation of space-based remote sensing observations directly related to the land surface. Hence the name CADAS SAT, because there is a CADAS that does not assimilate any satellite data. This version is an experimental system and has been running in operation since mid-2019. And it produces land surface analyses every 3 hours on the 2.5 kilometer pan-Canadian grid. So the different components. So CADAS is based upon an external land surface modeling system. So it's an offline system. It uses the soil, vegetation, and snow land surface model. And Vincent Viennet will talk about that later on. And SVS gives us a first guess of the land surface, which is used for the assimilation afterwards. For the atmospheric forcings, we use short-range forecasts from the HYDRODYNAMIC trial fields. And then along with those, CAPA is used to generate an ensemble of precipitation analyses. So we have two types of assimilations in CADAS, an ensemble Kalman filter for soil moisture and skin temperature. And you can see, for example, here on the bottom right, a surface soil moisture analysis for July 2020. And then for the snow component, it's an ensemble optimal interpolation, so a bit like what CAPA does, and related to snow depth. So here is a table really summarizing the current status, what we have now running, and what we propose as innovations in the recent initial innovation cycle. So soil humidity, we currently have SMOS data only, and as innovations, we want to add the SMAP data. For skin temperature, nothing has changed. For latency, I'll come back to snow afterwards. For latency, we went down from 9 hours to 6 hours. And the big change is, in the recent innovations is related to the snow data assimilation. So currently we assimilate snow depth data from SynopSWAB and METAL networks. So it's in-situ data provided throughout the year, well, when you have snow on the ground. Instead of doing this, now we assimilate IMS snow cover extent. So I'll now focus mainly on this subject. So why did we want to innovate in the snow DA? Basically because of hydrology. The hydrologists were not satisfied with the snow analysis in the current NSRPS. The snow assimilation technique, so the OI, is not conservative, meaning that when you have a negative increment, for example, in spring, when the land surface model is not melting the snow fast enough, a negative increment is applied to the background field, and the water is simply removed from the system. It disappears. A result of this is, you see the figure on the right side, it's the Ottawa River discharge at Britannia in spring 2019. In black, you have the observations, and in red, you have the simulated discharge. What you see is that we simply don't have enough water to simulate this spring freshet. So the routing system right now is avoiding this problem by using the control member. The control member is an open loop which sees no data assimilation. So it's really the land surface model that drives the routing system. And it's doing quite a good job, but we do want to constrain the land surface model and make use of the available observations when we can. So rather than correcting the amount of snow throughout the year, we want to correct the presence of snow. So that would be mostly in the transition season, so in the spring and fall. So what we do is that we use satellite-based IMS snow cover extent rather than in situ snow depth observations. So I suppose most of you are familiar with this product. It's a 1 kilometer daily product derived from a variety of products. You have satellites, in situ, and model data. It provides a binary snow cover extent, meaning that it tells you if there's snow on the ground or no snow. Because we wanted to have an innovation quite quickly, the technique, assimilation technique has not been changed. So here I'm showing you a few ways to evaluate the new analysis. So here I'm comparing to the IMS data. Obviously, this gives a large advantage to the new analysis. But we have used this evaluation in previous innovations, and I wanted to show it just to show that we're going in the right direction. So here you have 4 graphs that gives you the evolution, well, the evaluation of the snow cover extent from September to June, September 2018 to June 2019. The control in dark blue is what I told you the routing system is using currently, because the old analysis, so in cyan, was not doing a good job for hydrology. And in red, you have the new analysis. So as you can see, we're improving hits, reducing the false alarms in spring mostly, improving misses throughout the year as well. Correct no snow is no big change, but it's a positive signal all in all. So here we're comparing the snow water equivalent against snowtail data. So it's independent data in the sense that we're not assimilating this data. So again, same colors, dark blue, the control member, cyan, the old analysis, and red, the new analysis. And as you can see throughout the winter season, we're greatly reducing the negative bias compared to the old analysis. And it's neutral, if not slightly positive, for the new analysis compared to the old to the control member. Okay. Here I'm comparing the snow depth across the NSRPS domain against the in situ observations that are assimilated in the old analysis. So I'm only comparing 2 simulations here, the new analysis in red still, and the control member in blue. And as you can see here on the left-hand side, you have the mean error, so the bias, and on the right-hand side, the SCDE. You can see that we're greatly reducing the bias compared to the control member, so it's a positive sign because we want to beat the control member that is used right now for hydrology. For STDE, it's rather slightly negative or even neutral. The scale here is very small, 500 meters of snow depth. So yeah. Now, what we wanted to see is the impact on hydrologies. This is the old figure that I showed you before, where you have the observations in black and the discharge simulated driven by the old simulation. And this is what the new analysis provides for the river discharge at the same station for the same time. As you can see, we've greatly improved the discharge, and this is mostly because it's the new technique has been developed to optimize water conservation. without changing the simulation technique. So the next steps, well, we're waiting for these innovations to be accepted. So they'll first be tested within the NSRPS in a more operational context. And then well, I have to figure out a way to assimilate as many observations as possible, all the while optimizing water conservation. So right now, what I'm proposing is that we don't use in situ snow depth observation, which is a waste in a sense. We have data, we should make use of them. So I want to bring them back in, but finding a way to not cause problems for hydrology. So we want to use the snow cover extent from IMS, in situ snow depth from the networks we have, and maybe add to that. And we could even add SWE observations from Quebec and BC that we already have, and maybe soon we'll be able to obtain data from Ontario and Manitoba. And all this to go towards satellite data assimilation. So what we're doing in preparation for the assimilation of satellite data, first passive, then active when it will be available, is, as you'll see, Vincent Viennet will talk about this, we need a multi-layered snow model with specific snow-specific area simulated. We need a profile of this. We need to implement a forward model in CARDAS, so we chose SMRT, and Josh King is working on that at the Climate Research Division of ECCC. And all the while, I've been also assisting in the terrestrial snow mass mission called TSMM. It's a dual Ku band radar that would provide information with a 500-meter resolution with a 5 to 7 day revisit. It's a mission that's driven by ECCC and the Canadian Space Agency. It's currently in phase 0, and we're quite optimistic that it will go to phase A, and at CSA. And once it does, CSA says that it will be able to finance it all the way to the launch, the full mission. So the possible launch is 2026, plus a few years possibly. So that's it for me.
Thank you, Camille. So that was for the land data assimilation system. So now we'll go to Vincent Viennet. We'll talk about the land prediction systems. And in particular, he will talk about the land surface model that's part of this land prediction system, SVS. Vincent, the floor is yours.
Hi, everybody. Can you hear me?
Yeah, working.
Okay, perfect. So I will start sharing my screen. So as Vincent Fortin mentioned, this presentation will have like two components. I will first describe maybe I would say 3 components. First, the land surface scheme, which is currently used at the Environment Canada. Sorry, my PowerPoint is loading and it's taking some time, it seems, so I'm not sure you can see anything. Can you see the PowerPoint at the moment?
Yes.
Okay, excellent. So this PowerPoint is...
Sorry, cutting yourself. Your microphone is hitting on your...
Okay,
okay.
Thanks. So this presentation is about the SVS land surface scheme, the current model, as well as the future plan for research. And I will switch in the middle of the presentation to the operational system, providing like the forecast of the land surface scheme and how it's done in deterministic and an ensemble way. So I will try to be quick. It's a lot of information. This presentation is done with many co-authors working in the surface and hydrology group, both on the research side as well as on the development side. So you have heard about the SVS, which is the Soil, Vegetation, and Snow Land Surface Scheme, which is used as the operational land surface scheme in the NSRPS. And I just here presenting a very brief description of SVS. I would say that SVS is a land surface scheme that has been designed to provide efficient and robust simulation of the energy and water fluxes at the land surface for NWP and hydrological forecasting. It features a multiple energy budget for different types of surface for a given grid cell. So the model is taking into account snow-free background, snow-free vegetation, and when you have snow present in the grid cell, you could have a snowpack over background and low vegetation, and a snowpack which is below high vegetation that's going to be affected by different processes. If we now look at the different components of this system, for the surface energy, SVS is using like an approach which has been widely used in the, I would say, in the meteorological community over the years, which is the force restore approach. So force restore scheme I used to simulate the evolution of the ground and vegetation temperature. And this approach is also used for the snowpack schemes, which are used over background and low vegetation and under high vegetation. So it's a one-layer snowpack scheme. For the hydrology, there is an hydrology scheme that includes multi-layer in the soil to simulate soil water transport. And it should be noted that so far this model is not representing soil freezing and thawing and the impact of these processes on hydrology. So when you have such model, you can run it over a domain such as Canada. So you see here a simulation of a winter 2015-2016. You have the evolution of the snow depth, so the snow cover over the whole country, as well as the soil water, as well as the soil water content. So you see the evolution over the full years of these two variables. So the model is producing this kind of simulation. Here it's a simulation at 10 kilometers over Canada. And we did some recent tests with the model. So, for example, an evaluation of the snowpack scheme, which is still, I would say, classified as a simple snowpack scheme. It has been compared versus the ESM SNOMED database, which is a fantastic opportunity for snowpack modelers. It's 10 sites across the world. You have a lot of different years. You have a lot of data. So it's really very interesting to do detailed evaluation of snowpack model. We also compare it with a detailed snowpack model called Crocus. I will come back to that later. And overall, the model is showing overall good performance for SWE, snow density, snow depth and density as most of the open site, but is clearly showing issues at forested site due to a too simple approach to handle snow canopy interaction at the moment. And also SVS has been used in a recent collaboration with GWF. Actually, it's interesting. I lost one of my figures. So we did some high resolution hydrological modeling of the June 2013 flood in Alberta. So there was a collaboration between the ECC group and GWF. And we did some investigation on the sensitivity to the resolution of the atmospheric forcing and to the initial snow condition at the beginning of the flood. And it allowed us to clearly identify the need to have an improved snow analysis in the Rockies, so which is consistent with the work done with CAMI in particular in Caldas. So far, it's very difficult to take realistic initial condition for any application in the Canadian mountains at large scale, I would say. And now, I will switch to not where you have an idea of what is SVS. We switch to the operational implementation of the system in terms of the ability to provide forecasts relevant for hydrology with SVS. So this presentation now is given on behalf of my colleague Daniel Deacou. Can you see it now? It's a PDF. Can you see it?
Yes.
Okay, excellent. So this presentation is given on behalf of Daniel Deacou, who is the lead for the development of these two systems. So the name are complex. I think you have seen many acronyms. I would say in our DNA at Environment Canada to have a lot of different acronyms. So you have to keep in mind here that there are two systems providing forecast of the land surface. One is a deterministic system. You have one realization in the future, and then you have also an ensemble system, which is under development. So so basically you can see this graph that you have seen before. It's an overview of the system, and the HRD-LPS, so the deterministic component here is that's the forecasting component into the future, which takes its initial condition for CalDAS and is running SVS into the future. So there are two main motivations for the development of this system. The idea is to be able to provide like coherent, high-resolution, medium-range, deterministic, and ensemble forecasts of the near-surface variable, which are important for meteorology, temperature, dew point, 10-meter winds, and then within the context of hydrological forecasting to provide quality surface runoff, subsurface lateral flow, and drainage, which are necessary to produce then the hydrological forecast, as it will be illustrated by Etienne later. So this system, HRD-LPS, is the deterministic component is running in operation. The ensemble version is under development. So it's running the SVS land surface scheme in two stages. I will come back to that. I will come back to that now with these two graphs. So I would like you to focus more on the right side of this graph that shows how the system is working. So the deterministic component is producing forecasts until day 6, on the top of this graph. So you see that so it's running at 2.5 kilometers over the whole country. During the 48 hours, it's taking the forcing from the high-resolution deterministic prediction system, which is the operational system of Environment Canada at convective permitting resolution, so 2.5 kilometers. And then when you go into the futures towards longer time range, it's using the global deterministic prediction system from Environment Canada at 15 kilometers. And these forecasts are downscaled to the 2.5 kilometer resolution of the land surface scheme to provide a forecast over the same grid. The idea is the same for the ensemble system. You take forecasts. You take atmospheric forcing from ensemble system. So we are using the regional ensemble prediction system. And then when you go into the future after day 3, you take the global ensemble system. So it's the same idea. And then all these forcing are downscaled to the 2.5 kilometer grid. And with the ensemble system, you can reach every day. The idea is to have forecasts until day 16. And every week, the idea is to have forecast until day 32. So that's a system that will be operational in the coming years. You haven't on this image, you have an idea of how looks the domain. So it's the Canadian domain at 2.5 kilometers. So it's both systems are running on the ensemble, and the deterministic system are running on this domain. So you can see some like the level of details that you have in the mountain with the 2.5 kilometer grid, and you really see like a lot of, if you zoom, you see a lot of details in the mountains close to the coast and so on. So this model is able to capture this kind of small scales patterns. I think I'm not sure if we are running out of time at the moment or not. I may skip some of the details, but so the same as Dikra has shown for CAPA and Camille for CalDAS. So recently Daniel proposed some new innovation to the deterministic component. So the idea is to really be able to improve the result of this system. And some of the tests that were proposed are encoding near surface elevation and subgrid slope to improve the quality of the topography of the system. And then Daniel made some modification in collaboration with colleagues about how the stability of the atmosphere is handled when you compute the turbulent flexes, in particular to avoid one of the issues that land surface scheme are often suffering from in wintertime, this decoupling between the surface and the atmosphere. So basically, it's using a technique that allows to keep some mixing in the surface layer to avoid the decoupling between the surface and the atmosphere. I think I don't want to enter into the details. Basically, this system is improving the results mostly in the mountains of British Columbia in wintertime over snow covered area. And then I think it's too much details for this kind of presentation. And then you have here the first result of the ensemble forecast for over summer 2019. So far the system, the ensemble system in red was compared to the regional system, which is the operational system in blue. And you see that some of the scores are improved compared to the regional system, like improved RMSE as well as an improved CRPS. So it's really only very preliminary results, but so you have these two systems which are really like using SVS to forecast the future of the land surface. So both in deterministic and ensemble way. So I think that's the key aspect to keep in mind. And the deterministic goes to day +6, the ensemble until day 32 on a weekly basis. So if I now come back to so that's all for I would say the operational implementation of SVS. If I now come back to my initial presentation, I would like to present what are the plans for the future of SVS in terms of research. And the idea would be when we have when we make when we produce this development, the idea would be to test them within CalDAS as well as within the HRDLPS and its ensemble component. I guess yeah. Can you see my screen again?
It's not working.
Okay, and now my figure on the CAPA 1 kilometer is back. That's but anyway, it's no problem. So the idea is we really would like to move towards an upgrade of the land surface of the all land surface system. So so far we call it SVS2. It's not very original. It's a major upgrade of the current SVS. And the idea is really to keep the existing modeling architecture of SVS and like to be able to get modeling components, if possible, from existing other land surface schemes. So the idea is not to reinvent the wheel. It's more like to put together a component that have been well established and tested to be able to improve the system. So this the motivation is really like to improve some of the limitations that have been identified in SVS, in particular for core region processes. And the idea would be first to have a multi-layer diffusion scheme for the soil, for soil temperature, including freezing thaw processes and the impact on the hydrology. So because something that's missing in the current version of the model, and it's crucial for hydrology in Canada, but that's a key point. And then we would like to improve the snow physics, including a multi-layer snowpack scheme, and some of the improve the snow components in the model. I will come back to that later. A beta version of the model is available, so we can start working with it. So for the snowpack scheme, I think I will go quickly. The idea is to have like two kind of snowpack scheme because of my past, I would say, at the French Meteorological Institute. So far, we are proposing to use like two snowpack schemes that are implemented in the Surfax surface modeling platform of Météo France, with the explicit snow scheme first, which is a multi-layer snowpack scheme of intermediate complexity that would be suitable mostly for hydrological application. And then we want also to bring in our system the detailed snowpack model Crocus and its ensemble version. And the idea is to be able to have like a snowpack model that simulates snow metamorphism and the evolution of the microstructure parameters to be able then to compute some variables such as snow backscattering coefficient, to be able to do some work with the assimilation, as Camille was mentioned. So it's really in preparation of the future satellite mission that we're using this work with Crocus. We are working now on some development in SVS2 as well on the precipitation phase. So the idea is really is not only to improve the land surface scheme itself, it's also to improve like the input to the land surface scheme. So that's a current project that we have in focusing mostly in Western Canada, when we are testing different phase partitioning method and their impact on snowpack simulation. So we are using our SVS or present version of SVS2 with Crocus and we are running snowpack simulation driven by different PPMs. So, and you have here an idea of like how the different method of phase partitioning are impacting the snowfall fraction over Western Canada. And we are trying to also use some, not only like the classic approach using hydrology, using near surface temperature or humidity and combine them together to get wet bulb temperature. We're also trying to use like estimation from the snow level from atmospheric models, so more to account for all the information that can be bring by an atmospheric model to better determine the phase of the precipitation. And it will be extended to Eastern Canada this winter for the SAGES project, which is funded by GWF and led by Julie Thériault at UQAM. Future evolution, I will go quickly over them. We would like to improve the snow vegetation interaction. It's done in collaboration with colleagues from University of Saskatchewan and University Laval in Quebec to really improve because we know it has been identified as one of the weakness of our system. We'd like also to improve the subgrid variability of the snowpack, especially, for example, in mountainous terrain, and to use some of the nice products which are available, high-resolution products, to better determine this subgrid variability and to see how our model are able to represent it. And finally, we'd like to work also on Arctic snowpack because it will be important for the snow mass mission. And we need to improve the snow microstructure, which is poorly represented at the moment in snowpack models in the Arctic due to the absence of the upward water transport in the model. So that's all. So I would just to quickly, SVS is, I would say, an efficient and robust land surface scheme for our application in terms of land surface and hydrological forecasting. We have two operational implementation of SVS in forecasting mode, and one deterministic and one ensemble version. They are running over a common grid at 2.5 kilometers over the country and also over the northern US. And we have some ongoing development of an upgraded version of SVS named SVS2, which an emphasis on core region processes. So I would like to thank you for your attention, and if you have questions, I would be happy to answer your question. Thanks a lot.
So again, please ask questions through the chat, and we'll go to Etienne for the routing component of the National Surface and River Prediction System.
Yes, so hello, can you hear me clearly?
Yes, very well.
Okay, so I'm just switching to presentation mode, just checking that it works. Okay, so I will try to catch up a bit with the timeline a little bit. So I will talk about the DHPS, which stands for Deterministic Hydrologic Prediction System, and is the system component that is used to simulate river routing into lakes and rivers as part of the NSRPS system. So we have an assimilation phase and a forecast phase as well. So as Vincent Fortin mentioned, the full NSRPS system is also known outside of ECCC as the GEM hydro forecasting system. Vincent also already showed the current coverage of the routing system as part of the NSRPS. So the model, the DHPS, is based on the WATROOT model. WATROOT is a 1D hydraulic model that can simulate water level and stream flow inside rivers and lakes. It's based on a fixed grid resolution. Currently, we are using 1 kilometer resolution for all of our domains. And it relies on gridded parameters that are mainly derived from the drainage area of each, the upstream drainage area of each grid cell. And it also includes a low horizon storage compartment to represent base flow. So currently, this model is fed by the surface output fluxes, which consist of surface runoff, lateral flow, and drainage from the SVS land surface scheme, but also aggregated over the other surface tiles. And the drainage goes into the LZS before returning to the rivers under the form of base flow. So Camille already mentioned the issue we noticed when enforcing the DHPS with the CALDAS members that saw the in situ snow assimilation. which led to a strong underestimation of spring freshet, as Camille showed. Just wanted to nuance a bit what she said in the sense that we don't use the control member from CalDAS to force the HPS in assimilation mode all the time. We use currently, we switch from using the control member for winter and spring to using the median of the 24 CalDAS members that actually were impacted by the assimilation, like soil moisture assimilation, for example, to still benefit in summer from the soil moisture assimilation, which is beneficial to wet root. And as part of the current innovation cycle, where that will include Camille, the new snow assimilation method, we will actually most probably always use the median of the 24 members that saw the assimilation all the time, because this issue will be mostly fixed thanks to Camille's innovations. So just a word about the backward, the flow assimilation method we currently use in DHPS. It relies on direct insertion downstream of at the location of flow gauges, which impact the grid cells downstream of these gauges, obviously. But also we recently included a backward propagation method, which mainly consists in back propagating in the upstream direction the correction that the correction the correction that is computed for the gauge location. This has a significant impact on our scores. It has a beneficial improvement on forecasts, flow forecasts that can last up to a couple of days, actually, depending on the drainage area of the gauge. And so that's it. Just a quick overview of the recent and innovations that we are currently proposing for the HPS. The most important ones are this backward propagation, which is already included. Vincent Fortin also developed a new numerical solver for wet root, which allows to fast the solver a bit and leads to the more accurate average flow estimations. And in the innovations we are proposing currently, we are adding a lot of new flow observations from. So currently we were only using ECCC real-time gauges, and now we are going to assimilate as well USGS, so American stations, stations from Quebec province and Alberta. We are improving the flow assimilation method by also correcting natural lake levels based on downstream flow observations, in order to have corrections that can have a better, stronger inertia in forecast mode by correcting the lake level directly. We are also proposing a new reservoir model for regulated reservoirs instead of the natural lake model, and that's mostly it. So just an example to illustrate the coverage of the flow gauges we are currently using. With only ECCC, as you can see here, and now with all of the new gauges we are going to use as part of our innovations. So a much better coverage, especially in Alberta on the US sides and in Quebec province. So the natural lake level correction that we are proposing consists in correcting the lake level based on downstream flow data. You can have an example here of this effect. So on the left, you have an experiment. It's an hydrograph. So in black, observations, in red, simulated flow from the assimilation cycle of the HPS, and in blue, the forecasted flows. You can see on the left an experiment without the natural lake level correction, and on the right with this lake level correction. So it's working well, and it improves our forecast scores for all of our domains. For the DZTR reservoir model, it comes from actually the University of Saskatchewan. It's called the DZTR for Dynamically Zoned Target Release Model, and so you can look at the paper of Yassin et al. to have more information on the model. Just an example of the potential benefits. So here we are looking at hydrographs for for the Lake of the Wood outflows in the Nelson River Basin, and in black observations in blue with the natural lake model, and in red with the DZTR model. On the top, outflow, and on the bottom, storage simulation. So much better simulation with this new reservoir model. And an example in our real-time implementation of the HPS for the Mackenzie, for the Bennett Dam in the Mackenzie domain. On the right with the DZTR model, on the left with the natural lake model. So quite a strong improvement. So I also already did some successful calibrations of the full GEMHYDRO model, including the SVS land surface scheme and the watt-root routing model, as part of the, for example, as part of the GRIP-E project that is led by Julian May at University of Waterloo and Brian Tolson. And you can have an example here of the benefit of calibration for stream flow. Here we are looking at total inflows into Lake Erie in red after calibration. So of course calibration is important for hydrological simulations. Currently the SVS and watt-root are not calibrated inside the NSRPS, but it would my goal is to be able to bring some calibrated parameters inside of NSRPS, but not only to improve stream flow, also to improve surface scores as well with SVS. And you just briefly an example of the ranking, how we ranked as part of the GRIP-E project. So GEMHYDRO, we are looking at validation scores here. So special validation was done as part of the GRIP-E project. Julian May just submitted a paper on this research, and GEMHYDRO actually ranked quite well, and Mesh SVS, because we calibrated GEMHYDRO using Mesh SVS compared to other models that were globally calibrated, which are the models standing below the black line on this figure, all models which were globally calibrated as part of this project. So we are also proposing an ensemble version of the HPS that will be first delivered soon. So it's some technical details. We are using the same assimilation cycle as the HPS. So we are using deterministic initial conditions for the first implementation. And in forecast mode, it will be forced by the HRELPS, the ensemble version of the HRDLPS, so the surface prediction system. Such that we will be performing 16-day forecasts of stream flows once per day and 32 days once per week. And the RELPS, actually its ensemble configuration is based on the same concept. It will use first deterministic initial conditions and ensemble forecasts. And then in future versions of the system, we'll use ensemble ICs as well, and maybe other ways to produce ensemble forecasts. So in terms of research, as I said, we are also going to calibrate GEMHYDRO on the full Great Lakes watershed as part of the GRIP-GL project, which is the extension of GRIP-E, but to the full Great Lakes Basin. We are working on new evaluation scripts for the NSRPS for the stream flow, especially to be able to compute probabilistic scores for the new ensemble version of the HPS. And we'll also try to do some tests regarding the connectivity between surface and routing because of the related to the impact of lakes, actually the connectivity between the surface and routing in terms of lakes. So we have a new lake model that I will try to also somehow tune a bit or play with the coupling with the routing to be able to improve the forecasts, the stream flow forecast. We also proposed a project to assimilate SWOT data for lake level assimilation. And we have many things we have to work on, like also adding some variability to some parameters, like the lower zone storage compartment in watt-root, the SVS soil depth. So I'm also interested in working with SVS to improve some processes, like for example in the plains to use PDM rough routine that is used for class to better represent non-contributive areas. And we will improve the ensemble system, and also another area which we will have to work on at some point is the pre and post processing for an NSRPS, like by debiasing a precipitation forecast, for example, and post processing stream flow forecasts ultimately. So that's all for me. Thanks.
So that's great. We actually have a 5-minute break before we start with the third hour of the talks. So again, I encourage you to use the chat to ask questions. And I'm told that we'll be able to record that chat and continue so that we can continue the conversation offline. But if people don't need to run to the bathroom for 5 minutes, I'm happy to answer any question right now.
Yeah, so let's take 5 here. If you want to take a washroom break, that's great, but Vincent is open for questions. This is a big system, right? I hope people understand this is 20 years of work, kind of over many cycles, right? And the whole process too for approving changes to the code that, you know, Vincent can certainly discuss, right? This is not, it's a very formal process about changing code. You can't just kind of jump from one system to another, and because it's an operational system, right? So there's lots at play here, right? This is a bit superficial, I guess, from that perspective, but it's all great stuff, right? So yeah, any questions for Vincent, and we'll just ask the next speaker to load their talk, and we'll give people 3 or 4 minutes to take a break otherwise. And Vincent, I hope you're okay for staying on for a bit.
Yeah, absolutely. So I mentioned that in the chat. The tech transfers are done through innovation cycles, during which we have a chance to upgrade all prediction systems at the same time. And we're currently in the midst of innovation cycle 3. And when the prediction systems are upgraded, they are first run over reference historical periods called final cycles. And these reference historical periods are the same for all the systems: atmospheric, ocean, hydrology, surface. And they are then installed in operations and run in parallel for a couple of months at least, often much longer. And we are currently running these final cycles for the 3rd innovation cycle, and with a target of operational implementation in the fall. And normally this operational implementation comes with detailed documentation and products on our data mart, which is the website we use to distribute flat files containing the numerical predictions, and Geomet, which is the web services.
Yeah, I just Sal here. I think on that front, it's important for the researchers to understand, having run the Water Survey of Canada for the last 15 years too, right? We always get these, somebody comes up and says, oh, you should try this new technology, it's great. Well, it doesn't work that way in operations, right? You have to test it, you got to evaluate it. It takes sometimes years to get through moving from current meters to ADCPs as an example, right? It took us probably 10 years to move the whole system over. So these things are never trivial, right? So it's important for researchers to keep that in mind, right? You just can't say, oh, I got this great idea, let's implement it. It's nice, but it rarely works in operations, right? And so Vincent's team as a research organization really has to kind of balance all that out, right? So they're not an academic research organization, they're a government research organization. And so a lot of what they do with the close contact with the operational folks is make sure that, you know, they don't break the system, right? And so that's very, very important and good for people to understand. Okay, we can probably move to the next talk, Vincent, if that's good.
Yes, I think it's me. So let's see. Just to be sure. And next. So it's, I'll talk about the water cycle prediction system. I should have loaded it. My bad. So I just need to share my screen. So it's screen 1. Here we go. So the next talk is about the water cycle prediction system. So it's related to the National Surface and the River Prediction System, but it's different. We actually started to work on the water cycle prediction system first as part of the Upper Great Lakes study. So this is a system that was first designed for the Great Lakes, but it's been expanded now, and it also covers the Gulf of St. Lawrence, as you'll see. Again, there's a lot of collaborators on this talk, and especially there are collaborations with the ocean modeling group, because the lake model that we use for the Great Lakes is actually an ocean model. Oops. Okay. So I've shown this slide before. The water cycle prediction system is an operational 24/7 coupled atmospheric, hydrological, ice, and ocean model. It provides deterministic forecasts 3.5 days into the future, twice a day. The horizontal resolution is variable. So that's a feature here. We can have different resolutions for different components. And there's a coupler that handles the differences in the horizontal resolution and even temporal resolution. So we have 10 kilometers for the atmosphere. For the ice ocean, it's 1 kilometer for the Great Lakes and 2 kilometers for the Gulf of St. Lawrence. The routing model is at 1 kilometer. There are various products relevant to marine forecasts that are available on DataMart and Geomet. So water level, surface water temperature, current salinity, ocean mixing layer depth, ice cover, ice concentration, near surface atmospheric temperature, and wind. More products will be coming in operationally in the next year. They are already produced but not available to the public. This system has been documented in a paper in BAMS by Durnford et al. Here's the NEMO model configuration. This is our ocean model is NEMO. It's version 3.6 with a 1 kilometer bathymetry for the Great Lakes. It shares the same physics as the coastal ice ocean prediction system that Environment Canada runs on the East Coast. So it's the same physics. The river flows comes from what route, and it also includes the coordinated, a version of the coordinated Great Lakes regulation and routing model for lake-to-lake routing. Here's just a look at the what route domain. So all of the Great Lakes, but now extending all the way to the Gulf of St. Lawrence. That's the atmospheric model domain. So we used to have actually a system covering only the Great Lakes. The atmospheric model was this box, so centered on the Great Lakes, but much larger, so that our boundary conditions are far away from the domain of interest. There was another system separate for the Gulf of St. Lawrence, which so that was again a coupled atmosphere-ocean prediction system, but with no routing. So now we are merging the two, enlarging the domain of the ocean model. It used to be only the Gulf, and now the GEM model that is coupled to NEMO and WattRoute actually covers this whole area. So it's a big part of North America, except for the West Coast. There are products on DataMart and Geomet, so flat files and web services. And there's also a special report sent by email providing water level anomaly forecasts, significant wave height forecasts, and net basin supply forecasts. Documentation is available on GitHub. Innovations to be implemented in 2021 as part of Innovation Cycle 3. So the merge of the two coupled systems. an upgrade in the version of GEM, an upgrade in the version of NEMO, increase in resolution for the Great Lakes from 2 to 1 kilometer, upgrade in the version of the routing system, which will be nearly identical to the one we use in the NSRPS. The innovations as part of WattRoute are the data assimilation, so backward propagation that Etienne mentioned, new geophysical files, a new solver, addition of new observed flow data providers, especially in Quebec and in the US, the DCTR reservoir model. And there's this, so all of these are also in SRPS, but here we have a specific one for WCPS, which is the use of a climatological drainage that will come from the SVS land surface scheme. So the issue is that in this nice system, which is fully coupled, we're still using an older land surface scheme called ISBA that is used in the atmospheric models. So we are in the process of transitioning to SVS in GEM, but that's not done yet. So for this coupled system, we have to rely on this older land surface model, which does an okay job for surface runoff, but not a great job for drainage because it doesn't represent the soil moisture very well in the vertical. So here's an example of the estimated base flow component for the Ottawa River Basin. So this is obtained from flow observations and filtering technique. So in black, this is our estimate of base flow for that basin. With variability in Solomon here, plus or minus 1 standard deviation. And in green here is the base flow estimated by ISBA, which is way too sharp. And it does an okay job in summer, but a bad job in winter and also in spring, actually. So we can't live with that for WCPS. So we prefer to use a base flow coming from a climatology that makes more sense. This is the impact of using this climatological base flow in summer and winter. So these plots show the RMSE as a function of lead time of the forecast. In blue, the system that uses actually an older version of that climatology, and in red, this new climatology. So it's actually a bit worse in summer, but the differences are not statistically significant. And that's partly because ISBA does an okay job in summer, but in winter, it's really better, so RMSE is smaller. But these differences are small compared to the impact of all the other changes that were made to the system. So with the implementation in 2021, we'll have a much improved RMSE as a function of lead time in red here compared to the blue curve. And it has a lot to do with data assimilation. Here's a look at the impact on other variables. Here we're looking at the ice concentration. This is average over all of the Great Lakes. In black, these are observations. Red and blue are before and after the changes to the NEMO version, well, all of the upgrades to the system. So no notable differences for ice concentration or ice thickness. The SST looks good on average, but if you look closely, there are fairly large differences in the spring. So we think that the restratification is happening too fast in the model compared to reality. So this is something that needs to be looked at. The day-to-day differences can be, so from observations, we can have departures on the order of 10 degrees sometimes in terms of surface water temperature. So this is something that needs to be improved in the future. The system is used to look at storm surges. So this is an example of a fairly large storm surge for Lake Ontario, so at Kingston. You have much larger signals on Lake Erie, but for Lake Ontario, this is a pretty big one for Kingston. So in black, observed water levels at that gauge, and in the red, this is the forecast. So this is a 3-day forecast issued at the time here, or yellow bar is. So essentially, 2 days before the event, we could fairly well capture the signal in terms of water level. So this forecast is actually bias corrected on a real-time basis based on the recent past forecast. So this window on the left is used to remove any bias in the water level forecast. We also provide information about significant wave heights. So this is a plot showing the wave height. So the color is the probability of having significant wave heights of more than 1 meter. And the height is actually the height of the waves. So now, what about the impact on the weather? So we do this coupling to improve our lake forecast, but it actually improves the weather forecast quite a bit as well. So here is a comparison with an uncoupled version of the system. So the impact of coupling is positive when it's red. So these are the different variables. This is summer, this is winter. And this is an evaluation on stations in the Great Lakes vicinity. So here is surface pressure, dew point temperature, wind speed, and wind direction. So with the exception of wind direction in winter, we're improving things across the board, and especially for dew points, so humidity in winter, where we have an improvement of 8% in the changes in the standard deviation of the error. So quite significant. So in terms of research and development plans for this system, ongoing, there are case studies for lake effect snow and freezing rain events during the winter 2020. We want to, there are missing words here, we want to replace the coordinated river and reservoir regulation model. We want to replace ISBA by SVS. We're looking for this system not to improve the horizontal resolution of the atmosphere model first, but rather to go to ensemble forecasts with the plan of increasing the lead time up to 30 days. The coupling should have more impact in that context. And we want to assess the feasibility of performing a 30-year reanalysis. We're not sure about the cost of doing this. It's not sure that we can do this for the full 30 years, but perhaps we could do it on an event basis for cases where coupling actually matters. That's it for me. So the next talk is by Camille. We'll talk about another lake model that we use. So NEMO is used for the larger, well, the Great Lakes. We would like to use it for the larger lakes, like Great Slave Lake, Lake Winnipeg, perhaps Great Bear, perhaps a few more. But there are many more lakes in Canada where we won't be able to afford using NEMO, which is a 3D model. So there we want to use a simpler model, a 1D model called CSLM, the Canadian Small Lake Model developed by Mary McKay.
All right, thank you, Vincent. Can you hear me and see my slides?
Yes.
Perfect. So as Vincent just said, I'll be talking about a 1D lake model that Murray McKay developed and that we're putting in our systems currently. So what we have right now is NSRPS basically uses a very simplistic water model to simulate lakes and their exchanges with the atmosphere and fluxes basically. What's very important to note for the rest of the presentation is that ice cover and surface temperature are initialized once a day with an analysis that includes a simulation of satellite-derived and in situ data. So what that means is that when we don't have this new 1D lake model, we have a very simple model that is initialized with observed data basically, but you have to take care into the fact that satellite-derived data are mostly available on very large lakes and not small lakes. So for lakes that do not have observed data, we use a return to climatology. And within this very simplistic water model, we don't have a water budget. It's only, we provide P minus E to the routing model. So the objective here is that we want to simulate the state of the lake and its fluxes with a dynamic lake model, and eventually make use of lake-related observations in CARDAS. So the Canadian small lake model that Murray developed, so it's a 1D dynamic lake model, CSLM. Here's a graphic that shows you its different components, but I'll go over it quite quickly because I have only 10 minutes. So all in all, it includes a complete nonlinear surface energy balance and a water budget to calculate the discharge of the lake. So here I'm showing you a summary of the NSRPS domain related to the lakes. Okay, it has lots of information, but in the middle graph, you see in red is below 50 degrees north, in green between 50 and 60 degrees north, and in blue above 60 degrees north. And you can see that, for example, in our latitudes, about 34% of the grid points have some lake coverage. And if you go higher north, about 40% of the grid points have some lake coverage. And if you see on the right-hand side, here's a graph that shows you lots of numbers. But if you look at the subgrid, this is a matter of surface area. If you look at subgrid lakes, they cover up to 70% of all lakes above 60 degrees north, and even above 50 degrees north. So a lot of the lakes are subgrid shallow lakes, and these most of the time are not observed. We have no data on these lakes. So first, I ran a few simulations. The first one obviously is the reference run without CSLM. And the second run is with CSLM. So I evaluate the results against the IMS ice cover extent. So it's a bit like what I showed you for snow. It's a binary product. It's either ice or no ice. It's a daily 1 kilometer resolution product. And it covers mostly very large lakes. As you can see on the right here, you have 49% of the lakes that are observed by IMS are the 10 very large lakes of the domain. And then the remaining half basically are intermediate lakes between subgrid and large lakes. And so only 5% is left. 5% of the lakes observed by IMS data are subgrid lakes, so very few. So here I'm showing you the result of the evaluation. On the left here, you have different columns. The off experiment is one without CSLM, and the other two are with CSLM. So you can just, I won't go into what the difference between the two are, but it's not important for the message here. And what you can see is that hits and correct no ice are in green, and false alarm and misses are in reddish orange colors. And so we want more green basically. And you can see that for subgrid lakes, CSLM improves the representation of ice cover compared to when you don't have CSLM. For intermediate lakes, it's a rather neutral signal, if not a slight improvement. For large lakes, however, we degrade the result. But I'll remind you that for large lakes, we're competing against observations, basically, because the off simulation is initialized with an analysis that sees observations. So we're doing a good job on subgrid lakes, and intermediate lakes, but we're degrading the results over large lakes. Here we're looking at surface water temperature. So I evaluate against Sentinel-3 data because it's a data source that is not included in the analysis that is used to initialize the CSLM off simulation. But comparing the blue line is without CSLM and the yellow line is with CSLM. We'll only focus on the ice-free season because during the cold season, most lakes are ice covered and we have very few observations. In the warm season, however, we have no ice cover and we have a high confidence in both the observations and the model. And we see the signal isn't very clear for the bias. We see that we're going into a positive bias rather than negative bias. But there is a large improvement in STDE in both summers, which is a very good sign because here again we're competing against observations mostly, and for the RMSC it's slightly improved thanks to the STDE improvement. So here again it's a rather positive sign because CSLM is a model competing in this case against most observations over large lakes. So the steps here, step 1 was to implement CSLM in our surface prediction system, so SPS, which is an offline system, which is done thanks to Murray and Maria. First, we'll have to finish the current evaluation and write a paper, and then with Etienne, Murray, and I will improve the coupling with the routing scheme because right now we have some sort of discharge from lakes, but I think it could be improved for the routing scheme. And then the next step will be to implement CSLM in CARDAS so that we can prepare for the assimilation of lake-related observations such as ice cover and lake surface water temperature, and also to prepare for SWOT data, which will come in a year or so. It will give us information on lake water level and the extent of lake surfaces, which both could be very important variables. So once we'll have CSLM in CARDAS, we'll be able to assimilate observed data, and then we'll have really the best of both worlds, meaning that we'll have CSLM, which does a very good job, as we saw, over small lakes, subgrid lakes, where we have most of the time no observations, and we'll also benefit from observations over larger lakes where CSLM has more difficulties. So I think it's a project in its initial stages, but it's a promising project. So that's it for me. Thank you.
Thank you, Camille. So that's it for our lake models. We'll have now 2 talks on the hydrodynamic models, the model that is used for rivers. So the next talk is by Pascal Matt, who is the lead scientist for the hydrodynamic prediction.
Hi, do you see my screen?
Oui.
And do you hear me well? I guess so.
Yes.
Let's see.
Yeah, works when you go to full screen.
Okay. All right. So, so I'm going to be presenting the recent developments on the hydrodynamic forecasting system that we have that called SHOP. That's based on the H2D2 model. So this is a collaborative work between research, development, and also NHS. Actually, NHS developed the first version of this system maybe more than 10 years ago. So this is a continuing collaboration with NHS. So SHOP is a 2D hydrodynamic prediction system for the St. Lawrence River, and it provides depth average velocities and water levels at high resolution. So here's an example over Lake Saint-Pierre, where you see the definition we can achieve with this system. So a few model features for SHOP. It has drying wetting capacity that's based on the detailed bathymetry and LiDAR topography, so which allows us to represent very accurately the shallow topography for the intertidal flats, for example. So this is very important with tides, so that we can flood and dry those regions as a function of the tide. We also have spatial and temporal variability in friction that's based on the description of the bottom substrate composition, but also aquatic plants and the growth curve of each species throughout the summer. So here's an example of the spatial distribution of friction that can vary as a function of time. So this is for 3 different months in the year. So with a peak of friction caused by plants at their full growth. And also we have an ice cover extent that we represent based on static maps for different percentage of coverage that are based on CIS charts that we use to define thickness and roughness on each grid points of our model. So this is all carried by a 2D finite element mesh. So you see higher resolution around structures, for example, that have an influence on the flow. We also have a finer detail in the node channel so that we can represent those elements very accurately. Oops, sorry. So here's the current configuration of our system. There are currently 2 branches, one smaller branch, which is the analysis branch that covers a smaller domain from Montreal to Trois-Rivières. It's a steady state solution, so it provides daily analysis. And then there's a larger domain that extends upstream up to Carillon-Beauharnois, upstream of Montreal, and then downstream to include a tidal river. So it's influenced by tides, so we run it in unsteady state mode, and we have a continuous analysis cycle that provides initial condition to 4 forecasts of 48 hours per day. So those different elements highlighted in red here are the components of the system, or the inputs to the system that will be modified in the next innovation cycle. So for now, the tides are forced by a DFO model called SPINE. We take inputs from WCPS and temperature from CAPA for the ice cover. And so those will be changed in the next few slides. I'll describe those modifications. So basically what we want to do is to you take our SHOP system and then implement it as a component of the surface and river prediction system. So this is going to be basically coupled to we'll receive inputs of river inflow from the DHPS, and also winds and temperature from the CALDAS system in analysis mode, and HRDLPS in forecast mode. So the analysis cycle here provides initial conditions to the forecast, and then we use water level observation or harmonic prediction for water levels, depending on the analysis or forecast mode, and then SHOP produces forecasts of 2D water levels and currents. So the innovations per se are related, as I said, to those 3 components in red. So basically what we want to do is replace the water level boundary conditions from SPINE to a new harmony boundary condition that's composed of a tide component and a residual or surge component. We also replace the WCPS by the HPS from the National Surface and River Prediction System, and then we switch the temperature observation from CAPA to the CALDAS system. And all this is implemented in a new Maestro suite that's more robust. So I think the most significant change that we've made that has the most impact is the change of the boundary water level boundary condition downstream. So basically, SPINE is a 1D model from DFO that has tides that are not that are tweaked and distorted so that it behaves well within the 1D model that they have. But when we use that forcing for our 2D model, it basically propagates the wrong tide and affects the total water levels for the first 200 kilometers of our system. So this is quite a huge problem. So we decided to replace this model by a simple forecast of total water levels that's composed, as I said, of a deterministic tide and a statistical surge. So again, total water level is the prediction. The first part is tides. That's taken from harmonic analysis, so this is easy to get. And then we also add to this statistical sine wave that's fitted with observation for the residual. So this residual here is the observed residual is presented in yellow, and the predicted one is in purple here. So this is the water level here and the 48-hour forecast. So we first forecast the residual and then we add it to the tide forecast to get a total water level forecast. So in red, you have the total water level that we forecasted for those 2 days, and then compared with the observation in blue. So it performs quite well. At initial time of the forecast, the observation is the prediction is exactly the same as the observation. So that's a seamless transition between the analysis and the forecast modes. So here's the result for the nowcast. So this is for 2 stations in Quebec and Batiscan, which is 100 kilometers upstream. So you see that the water level, so this is for a 2-month period, summer months, July and August. So the nowcast is in red and compared with observation in blue. It performs quite well, reproduces well the variability of tides. Huge variability in Quebec, and then smaller tides in Batiscan, but a larger variability in mean water levels caused by the river discharge. So now here I present the root mean square for total water levels as a station average over the 2-month period. On the left is the results with the previous version of the model forced by a spine, and then the new harmonic boundary condition. So what you see here is the RMSC as a function of distance to the downstream boundary conditions. So here is the Baie-Saint-Paul or Saint-Joseph-de-la-Rive station downstream, and it goes up to Montreal here. So in blue here, you have the errors for the nowcast. So the 2 figures here were the nowcast at 2 stations. So now you have the errors, the average error for each station in blue. And then you see errors for the first day and second day for forecast. That increased significantly in that case for the previous system. So you see a huge increase in the error for those stations 200 kilometers from the downstream boundary. And then when we replace the downstream boundary condition by a better representation of tides, then the error significantly reduces, very close to the error in the analysis actually. So this is a huge improvement. Now, the second improvement that we implemented is the replacement of WCPS by the DHPS from NSRPS. As Etienne showed earlier, it includes several changes. It has more observations, mostly from the province stations. It has a new data assimilation system, a new reservoir model. And when we switch from one to the other, in our case, here is the same similar graphic for the first and second day forecast for the station average again. Comparing in blue is the result with the HPS, in orange from the previous WCPS forced system. You see slight improvements at stations upstream. The second day it's more visible, but it's very slight, but still we're going in the right direction. It's improving the system slightly. So in conclusion, SHOP became the first 2D hydrodynamic forecasting system for the St. Lawrence River in 2019. Now we're presenting new innovations, improvements on the tide and surge representation, also in connection to the NSRPS for now in terms of discharge only, and then a more robust suite to implement those changes. the ongoing and future work, we're going to connect our system again. Again, within the NSRPS, we will use the wind fields from CALDAS and HRDLPS. Eventually, we will change the boundary condition to use the coastal ice ocean prediction system, tides or surge. We will soon add new domains, starting with Lake Erie and eventually Lake Champlain. And we're going to be working in research on improving the representation of ice, and also developing a first prototype for ensemble forecasting for Lake Champlain. So this is this opens to the next presentation made by Sylvia. So that's it for me. Thank you.
Okay, so we have one last presentation today on ensemble forecasting of water level. This is ongoing work that will be presented by Sylvia Innocenti. So Sylvia started to work with us, I guess a bit more than a year ago, but on a different topic. But she's been recently working on this topic of ensemble hydrodynamic forecasting. Sylvia, the floor is yours.
As usual, do you hear me? You can see my screen and see slide?
Yes.
Okay, so hi everybody. Okay, so as Vincent said, in this last presentation today, I will try to give a very quick overview and really not technical overview of this new project that just started in our team, which aims at producing ensemble forecasts in hydrodynamics, and in particular for lake water levels and currents after. So why predicting lake water levels? Mainly because we are interested in extremes water levels, since obviously these extremes may have important impacts on human societies and ecosystems. But particularly because these impacts may strongly depend on the spatio-temporal characteristics of the water levels, namely where, when, and how these levels occur. Also, note that in this project, we will be mainly interested in extremes, which will be driven by intense meteorological conditions that last for several days. Namely, we will try to produce predictions at medium range horizons. Why these horizons? But mainly because those are the kind of extremes that present an interesting spatio-temporal structure. So here the point of using hydrodynamics ensemble forecast. So basically the main point will be to recover all the relevant components of variability of extreme water levels. And this basically means that we have to assess how the hydrological and meteorological variability propagates through the basin to the hydrodynamics of lakes and then maybe back to the river. To give an adequate representation of this uncertainty, the first step will be to directly use the NSRPS system, the National Surface and River Prediction Systems, in its ensemble version, namely exactly the same system that Etienne just presented, which is able to produce ensemble forecasts for streamfall. And this ensemble forecast will be directly injected in the H2T2 hydrodynamic model, which is the model that Pascal just presented. And this will basically produce an ensemble for water level prediction. But obviously, it will be also important to include another component of variability, namely the component speaking about all the direct impact of weather over the lake surface. So this will be probably produced by perturbing the wind and precipitation fields that are injected into the hydrodynamic system. Obviously, a first step will be to give an evaluation of the system, but then the continuous improvement of the system will lead to the refinement of this structure. So, in terms of case studies, a couple of experiments have already been defined for testing these forecasts, this forecast system. all these experiment concerned with the Lake Champlain and Richelieu River watershed. Why this basin? Basically because of its characteristic position, shape, and topography. Because really you can see the very stretched, long shape of the lake. Is typically connected to characteristic weather pattern over the surface. Here, for instance, an example of a wind field for an extreme occurring in 2011, which are typically connected with a characteristic distribution of water level extremes. So here, the interest for our project. Also, this basin recently experienced large floods in recent years. So it is actually a very important focus of both US and Canadian government, since the basin is transboundary with most of the lake is in the US, while the outlet and the river flows in Canada. So here again, the interest of simulating and predicting the hydrodynamic of the system. So in terms of periods, we, for the moment, we identified at least 2 interesting periods to study this system. One in 2011, one in 2020. Both the period are related with the transit over the basin of important meteorological system. For instance, in both cases, we observed actually the tails of 2 hurricanes passing over the basin. And though this transit give us the possibility of studying interesting feature for hydrodynamics. For instance, here you can see in both graphics that as soon as the system pass over the basin, we can observe a very quick rise of water level. But what's interesting here is the fact that the rise is different at different points over the lake. Namely, here I'm presenting a point in the south, a point in the mid, and a point in the north of the lake. So we really observe differences in water level that are directly driven by the effect of precipitation. And similarly, we can also see some effect of winds. For instance, we can see the oscillations here in the series. But again, the interesting part is that these winds really affect the system locally. So it's for this kind of event that we want to construct hydrodynamic prediction. So unfortunately, I don't really have analysis or result to show since the project just started. Some preliminary analysis have already been done by Pascal and other people from the NHS. But here for today, for this presentation, I will just thank you. I don't know, looking forward to tell you more about that. That's it.
Thank you, Sylvia. So we'll be looking for results in a year or so, I guess. This is an area of active research, as you see. There are many ensemble prediction systems for stream flow that are operational in various centers around the world, but not that many for water levels yet, especially for complex systems that are affected both by precipitation and wind. So Alain, back to you.
Yeah, great, thanks. So a couple of things maybe before we close off here. So thanks everybody for the talks. That was brilliant, and thanks to Vincent especially for organizing it on behalf of his team and to benefit all of us. A couple of points I think that need to register here, and I'll ask Drew maybe to make a few points as well with respect to the POWEL project. But you know, in Canada things are a little different, right? With respect to flood forecasting, right? This is all about developing a prediction system. We will be working with the provinces to kind of make sure they get the information they need. It's not Environment Canada's responsibility to issue a flood forecast, it's the provinces, right? But there's no way the provinces are going to develop this kind of infrastructure on their own. It's just too difficult and it doesn't make a lot of sense. So really it's a partnership with the provinces that we're trying to build here, where they take advantage of what we can do in ECCC, international structures, and then take those products and services and move them forward. On the transboundary side, it's always a little bit trickier because there is a federal role there, just like there is with the Army Corps in the US and NOAA and others. We're trying to navigate that reality. We're not exactly sure how it's going to proceed, but we do have an MOU with NOAA to look at some of these things, right? And so we are planning a fairly large prediction workshop virtual in February with NOAA, with all the provinces and territories in Canada. And we might get the IJC involved as well. We've been talking to them. So a 3-day workshop to kind of bring some of this together to report back to these entities on what we're doing within ECCC, where the research is going. This will be another GWF hosted workshop. And we'll have some US counterparts at the table at that meeting as well, right? To discuss where NOAA's going with their WRF system and how we can bring the two together on the transboundary, right? So that'll be coming, and certainly Drew will make you aware of that meeting because you have a long history with that group anyways, so that'll make some sense. And we'll see where that all goes. So this is kind of an overview of the research, and hopefully folks are understanding the bigger picture here, right? This is a big deal for Canada. We haven't done this before, and we're trying to move this forward. We're also discussing in Canada a movement to a Canada Water Agency. I'm not exactly sure what that's going to look like, but we need to be prepared for that political decision when it comes, right? The Prime Minister did commit to developing a water agency. It's on the books, and we're just not exactly sure how it's gonna fly. So we're reaching back to folks in NOAA and to the USGS to kind of see what the experience has been like in the US, and trying to sort that out for the Canadian side. So if anybody has any brilliant thoughts of what an agency should look like, let me know.
Or call the Prime Minister.
The last point, that I know for the PAL folks, this might have been a bit pedantic and a lot of details, but hopefully it was helpful. Your objectives are a little bit different, and I get that. But I think my view is a lot of the products that we're developing here, some of the snow products, the operational products, CAPA, all those things might be useful as inputs into some of the models that are going to be developed under PAL. There's lots of opportunities, I think, for synergy. So I hope it wasn't, I hope you saw some value in this thing. And so with that note, I'll pass it to Drew to maybe talk to his PAL folks about this meeting, and then I'll close it off at the end. You're on mute, Drew, or we can't hear you. I'm not sure.
We can't hear you.
You don't appear on mute, so somehow.
Must be your microphone. Not working.
Oh, well. Yeah, I don't think it helps if you scream louder.
You could write something in the chat.
So Brian's giving you a hard time there. So I'll let Drew type up a little note for everybody from the PAL perspective. But we'll keep you posted on the upcoming meetings. And again, thanks to Vincent and his team for this. As I said, we'll let you know this is all recorded. There's a really long history of collaboration, Canada, US.
I think we can hear Drew.
There you go. Okay, Drew.
So sorry, Albert, is this working?
Yeah.
Okay. Al, do you mind if I take just a moment to respond to your request very quickly here?
Floor is yours.
I do not feel like typing what I want to say here. So first off, thank you again, folks, for extending the invitation to the Powell Center team. I will argue, Al and Vincent and others, that it is absolutely invaluable for the Powell Center project, and quite frankly, any scientist in the Great Lakes region to be exposed to the incredible work that you're doing. Vincent, you and I know, and Al, we've talked about this for years, that there are huge gaps in knowledge across the basin from folks that say they are hydrologists or hydrometeorologists who aren't aware of the full range of products. So this is absolutely invaluable. And I'd say especially for many of the young scientists on our team, including the Powell Center Fellows, who have a lot of research on a global scale or even a continental scale, but have never understood fully the range of data and modeling products available to them. And so again, I want to underscore that knowledge of your product is absolutely critical to the Powell Center project moving forward, particularly as we get to understand what the role of groundwater is in all of these modeling and data systems at different spatial and temporal scales. So I just want to underscore again, thank you for this opportunity. I hope you're willing to stay in touch. Al, of course, is a member of the Powell Center team, but we look forward to staying in touch with other questions and future collaborations. So on behalf of the Powell Center group and many other scientists, thank you.
Great. Okay, thanks, Drew, for those thoughts. And yeah, I second everything you said there. This is wonderful. So yeah, with that, I think we're done here. So thanks again to everybody for doing a 3-hour Zoom call. Those are tough. I'll plead with everybody, please stay safe. Enjoy the holiday season coming up. And we'll send you more information with time, and we'll also send Drew at least some information about the upcoming meeting we're having with NOAA and our provincial forecasters. Maybe a few of the Powell folks might be interested in attending that as well. So yeah, let's keep the communication lines open and onwards and upwards. Thanks, everybody. Take care.
Thank you again.
Thank you.